So, good morning, everybody. It's lovely to see the room really full of people. And I had a great time at the conference yesterday, and I feel sure that we're going to have a very fascinating session today, going from spiking neural networks through deep neural networks, neuromorphic computing, with presentations from academia and from industry. I'm super fascinated to find out the latest research in these areas. To start us off this morning, we have Robert Legenstein, who I don't know if he knows this, but who has been quite influential on the way that I think about spiking neural networks and the direction of research that I've taken. So it's a particular pleasure for me to welcome him to start off the session. Please tell us about extending the capabilities of spiking neural networks. Robert Legenstein from the Technische Universität Graz.
Thank you so much, Abigail. Today I would like to talk about, as announced, spiking neural networks. And in fact, I want to tell a story about the evolution of spiking neural networks and how we recently tried to extend their capabilities. So basically, it all started in 1943, when McCulloch and Pitts introduced the first mathematical model for a biological neuron, the so-called McCulloch-Pitts neuron. This neuron model has n inputs. It doesn't have weights, but it has a threshold, and it has excitatory and inhibitory inputs. And when the number of active excitatory inputs exceeds a threshold, and there is no inhibitory input active, then it outputs 1. So it's a binary neural model. And McCulloch and Pitts tried to use it to show that computations in the brain could be seen as digital computations, like in a digital computer, like in a Turing machine. However, what we're doing now is kind of the reverse thing. We try to understand computation in the way how the brain computes, which is probably quite different. When you try to train networks of such neurons, you run into problems, at least at this time, because of this discontinuity, which is not differentiable. So what people did was they were actually replacing the activation function with a differentiable activation function to get a differential neural model, and you can use this in neural networks. And these are basically currently the neural networks that you have in deep learning. So I see there is a problem with the slides. There should be weights here. Actually, hopefully we won't have more of these problems. Then people were trying to look at neural models which are more closer to biology, and the spiking neural models were introduced. In a spiking neural model, they have also binary output, so the output is a spike train, the inputs are spike trains, and the most important difference is that they compute in time. So they use time for the computation, and there is a temporal integration, a leak integration of the inputs. Quickly, the most important today, maybe spiking neural model, is the leak integrated fire neural model. And so you have input spike trains. They are weighted by synaptic weights, and then they're added at the membrane potential, and the membrane potential does a leak integration. So the membrane potential is increased with its spike, and then if there is no input, it decreases exponentially. It's just an exponential filter. But when it reaches the threshold, then an output spike is produced. Okay, so in the late 90s, Wolfgang Maas showed that networks of spiking neurons are strictly more powerful than networks of artificial neurons. He did this by first showing that you can, with a suitable spiking neural model, you can basically map each artificial neural network onto a spiking neural network with the same number of gates. Right? This is one direction. But in the other direction, you can show that there are functions which you can compute with a single spiking neuron, but you would need a network of neurons to compute that if you have artificial neurons. And this is one of these functions. This is the element-wise distinctiveness function. It has n inputs from R plus, or positive real numbers, and it should output 1 when you have 2 of those inputs, one pair, which are equal or close together. You could also have some epsilon difference here. It should output 0 if they are far apart, like each pair is at least some constant apart. Here this constant is 1, and it's arbitrary otherwise. So basically we want to know if there is a pair of inputs which are approximately the same. So with a spiking neuron, it's very easy to compute it, really straightforward if you use a temporal code. So in this temporal coding, the larger this input x is, the earlier is the spike. So you have a linear mapping from a real number to a spike time. And now if they are all far apart, each pair, then if you sum up, like if you use a leak integration, you won't reach threshold, right? But if I move now, let's say this spike here closer to this spike, I will do this for you, right? They integrate in time, and you reach the threshold and the neuron spike. So that's simply the way how you compute this function. However, Mas showed that if you use a network of sigmoidal neurons, you need at least n minus 4 divided by 2 minus 1, so O of n neurons in the first thin layer of this network. So this means that spiking neural networks are strictly more powerful than artificial neural networks. But what does this function tell us? First of all, it tells us that you can really utilize time for computation in spiking neural networks. And spike timing is important. Basically, in the computation that's done by this neuron, you do a coincidence detection, right, of inputs. And if you use, in addition, delays in the synaptic connections, then you can also detect spike patterns, temporal spike patterns, really. So therefore, we believe that spiking neural networks should be really excel at temporal processing tasks. Now, the history evolved, and of course, deep learning came up. And with deep learning, kind of the game changed a little bit, of course. We saw that we can train artificial neural networks, deep artificial neural networks and huge artificial neural networks with gradient descent and backprop. And so the question was, can you do similar things with spiking neural networks? So the first attempts were to do a conversion, right? So basically, you can take an artificial neural network and convert it to a spiking neural network using a rate code. Basically, the analog output of a ReLU gate would be transferred in the rate of a spiking neuron, and then you can do basically the same computation. And there have been several improvements on that, and here is a figure from Rickauer et al., which shows that you can get very close to the performance of artificial neural networks. However, this rate coding is really inefficient. You don't want to encode a real number with a spike rate. That's not what we want. So you want to utilize the temporal properties of spiking neurons. So it would be good to train spiking neural networks with backprop, for example. And this has been done. Actually, this training idea started much earlier in 2000 by Sander Bottet, who introduced SpikeProp. But SpikeProp is kind of limited in its application to deep neural networks, so people are looking at different approaches. And the solution is basically surrogate gradient training. So surrogate gradient training starts with this problem of spiking neurons. So you have a nonlinearity, actually non-differentiable nonlinearity at the output of a neuron. When you think about the spiking output, as a function of the voltage, it's just a step function. When you're below the threshold, output is 0. When you're above the threshold, output is 1. You spike. And this is not differentiable, at least not useful. So the solution is just to invent a gradient here, which is called the surrogate gradient. So typically, the surrogate gradient looks like somewhat like this. So it increases as you get closer to the threshold. It turns out that this works really surprisingly well, and you can now train spiking neural networks. So one thing you can also do is to first convert an ANN to an SNN as before, and then train it afterwards, and this quite improves the performance, as well as you can become also efficient, which is shown here in terms of the number of times that you need for the computation. So this is nice. But in fact, these are like convolutional networks. They're feed-forward and stuff. And so I'm much more interested in recurrent networks. The main reason being that if you look at the brain, it's full of recurrences at any spatial scale. Yeah, from the global scale of areas down to the scale of microcircuits, you see recurrences. So we should really look at recurrent neural networks. And yeah, the problem is if you train a recurrent neural network with surrogate gradients, a leaky integrated fire network, it doesn't really perform well. So here is actually a simple task. This is sequential MNIST. And so you have the MNIST data set, but you don't show the image at once to the network, but rather you show one pixel after the other. So you get a temporal sequence of pixel values, which you encode as spikes. And in total, you have like 700x time steps. And then in the end, you want to know what digit was shown, right? So if you take a live neuron, and we tried it and train it, it just doesn't perform. It's really bad, right? It's much worse than if you take just the standard RNN, or when you take an LSTM, you're much better, right? So what's the problem? So one problem is that the temporal integration of a leak integrated fire neuron is very fast. So it's on the time scale of milliseconds, so tens of steps here in the sequence. And you could, in principle, do temporal integration with the recurrent weights, but training the recurrent weights is really hard. So you have the vanishing gradient problem, you have the potentially exploding gradient, so this is problematic. So what you really want to have is some kind of longer timescales in the neurons themselves. And in biology, you find that. So there are many neurons in cortex and in the brain which are adaptive, which means if you show a constant input current, the firing rate will adapt to that. You don't have like a constant interspike intervals as you would have in leak integrated fire neurons. So what we did was we extended the live neuron model to be adaptive. The way we did it was firing threshold adaptation, so that for every output spike, you increase the threshold a bit, which makes it harder for the neuron to spike, which leads to this adaptation. And the time constants for this adaptation variable are on the order of hundreds of milliseconds, maybe even seconds, in cortical neurons. And so this is a nice time scale for this type of computation. And if you do that, you can drastically increase the performance of spiking neural networks on this task and get very close to LSTMs. This was kind of the first approach to do that, and people came up with alternatives which are even better. So this is another neural model which was introduced actually in 2001 by ICNCE, where he wanted to model different types of neurons in the brain. There are also these resonator neurons in the brain. And if you look at the impulse response of this neuron, it looks quite different from the leaky integrated fire neuron. This is just an exponential filter. Here you have a resonator, really, which has some eigenfrequency. And you can model this very easily. So this is the leak integrated fire neuron, subthreshold ODE, right? And you subtract an adaptation current, so you need another second variable for that, right? And then you get this coupled system where this adaptation current increases as the voltage increases, as well as with each output spike shown here. But this has implications that you get these oscillations here, and they can be used for computations. And now you see that if you have two input spikes, and the second spike should kind of have a maximal influence on the memory potential, it should come like close to this eigen frequency or this period here, right? So it's a different type of computation. And people were looking at this, so Botte again and Bitter and Gunner, for example, very recently, and showed that if you take these types of neurons, you can improve over the adaptive neurons that we used. So here is an example, and for this data set, the spiking Heidelberg digits data set, a data set about spoken digits encoded as spike patterns, you can even surpass, as they show here, yeah, the state-of-the-art of artificial neural networks on that data set. This is quite interesting, we thought, and we would like to understand why this happens and what happens in the network. So we were training neural networks consisting of live neurons and another network consisting of adaptive live neurons or resonator neurons. And then we used tools from explainable AI to find out what is the optimal pattern that would optimally activate one output class of this network, right? So say the class 3. Yeah, and such optimal patterns are shown here for leaky integrated and fire neurons, and this one for resonator neurons in the network. And you can see very surprisingly that for the live neural network, there is actually no temporal structure in this pattern. This is surprising because we thought we want to use live neurons for temporal computation, but there is no temporal structure here. For the live neurons, for these adaptive resonator neurons, you see nice temporal structure, which is really what we want to have. Okay, talking about structure, I would like to talk about neuron structure now. Yesterday we heard about the dendrites, yeah, and that they're really important for biology. And I can say, yes, they are really important for biology. But what about neuromorphic computing? Can they be important for neuromorphic computing? So neuromorphic computing, I mean, the dendritic structure of a pyramidal cell is quite complex. We don't want to implement this complex structure in neuromorphics. So what we were thinking is, take the minimum neural model that kind of captures the behavior that we get from biology and see what it can do, right? So if you look at a pyramidal cell, this is a kind of a pyramidal cell, and it has two main sites of integration. At the basal dendrites, the soma, you get feed-forward inputs from sensory systems or from lower-level cortical areas. And at the apical dendrites, here, the neuron gets feedback feedback information from higher-level areas, mainly. And this means that the way how this neuron should compute is, and this has been shown that it's kind of a context-dependent computation unit. So it gets context here, and the context modulates how the inputs are integrated here at the soma. Our simple model that we used to model this has two compartments. We have two leaky integrators, one at the somatic side and one at the apical compartment. And by Larcom and others has been shown that what really happens is that the output firing rate is modulated by this apical activation. So when you increase the apical activation, you get a higher gain of the neuron response, which means you have a multiplicative interaction. So this is what we modeled, a multiplicative. We take the activation here and here, we multiply it to get the output spike train. Then we take that neural model, put it into a recurrent network of neurons, and see what it can do. We train the whole thing with backprop through time. So we wanted to look at a context-dependent computation task. Here we provide context, and here we provide, let's say, sensory type of input. The sensory type of input was from DVS gestures, so which are kind of spike patterns. We have different classes. So for example, a gesture that was shown in front of a DVS camera would be an arm roll or air guitar or hand clap or something. And now we show a sequence of those. And the context tells us to which gesture we should at which gesture we should output 1. So this would be air guitar here. So this is the target. And then we also want to remember that over the whole sequence. Yeah? Now if you train a network of, these are our threshold adaptive neurons, yeah? Adaptive neurons even. On this task, it completely fails. So this is chance level performance. However, if you take our context-dependent models of pyramidal cells, they perform much, much better and perform really quite good on this task. Yeah, this shows that a very simple change of a neural model and this one multiplicative interaction that you have here really can improve the performance of your spiking neural network quite a bit. And actually, if we use an additive interaction here, yeah, then you fall back to very bad performance. So the multiplication seems to be really important, which we actually know also from other models like transformers or LSTMs, which use multiplicative gating. Let's switch the gears a little bit and talk about learning. So we train our networks with backprop through time, right? But backprop through time is really bad in terms of implementation on neuromorphic. So we were asking ourselves, could we get an algorithm which is better suited for that? Let's look at the dynamics of backprop through time. In backprop through time, for a recurrent neural network, you cannot compute directly the gradient. So what you do basically is you unroll the network computation in time. So for every time step of the computation, you get one additional layer, and you get a virtual feed-forward network. If you have 1,000 computational steps here, the depth of this network will be 1,000. Yeah? And then what you have to do is you have to remember all the states that you had during this forward computation. And when you do the backprop, you use that to compute the gradients. So this means you kind of really have a locking problem here, because to compute the gradients, you have to store everything you had before. And this is really hard to implement in hardware, as well as I cannot imagine that the brain would use such an algorithm. OK, so what can we do? Well, you look at the equations for the gradient, so the error with respect to the weights, and then you kind of rearrange sums here, and what you get is this equation. You don't have to understand it, of course. But what I want to say is that it consists of two parts. This part here, you can compute completely online feed forward. You only need the forward path for it. And this term we need to compute for every synapse or every neuron, depending on the complexity of a neural model, but let's say for every synapse. So this is this eligibility trace here for a synapse Ji. We have to compute this eligibility trace, but this is just a straightforward, like filtering, basically, of pre-postsynaptic activity. It's very simple to compute. And this term here, you cannot compute online. However, you can approximate it. So we approximate this simply by an instantaneous error signal and use that instead. And the resulting algorithm is called eProp. And eProp actually now can be computed completely online feed forward. And this was work by Guillaume Bellec. And when you do that, you can use it, for example, for reinforcement learning, and you can train a spiking neural network to play the game of Pong and succeed in the game of Pong. So I told you that this algorithm can be implemented in hardware, and there is a proof for that, because colleagues from ETH Zurich, Charlotte Frankel at this time in the group of Giacomo Indiveri, they implemented this algorithm on a chip, which they call Recon. This was in a project where we were working together, and very nicely showed that it can do nice learning on chip. So another topic is memory. We talked already about timescales, and I said that time constants are really important. If you use longer time constants in your spiking neural model, this improves performance of your networks. However, when we think about timescales in the brain, there are much more timescales. We also have memory, which is timescale of computation on a very long timescale, right? So in our network models, we don't use that, really. In this work, we were thinking about what if we include kind of memory modules in our spiking neural networks. So memory is believed to depend on changes of synapses in the brain. So you have synaptic plasticity, long-term plasticity, which changes synapses, and therefore you store information there. And that's what we did here. We used kind of the simplest model of a memory, which is a heteroassociative memory. It's just two layers of neurons and synapses in between. And then we use a Hebbian type of plasticity rule, which is given here, to change the weights of the synapses. So basically, just a synapse is increased if the pre- and postsynaptic neuron are active. So the synaptic weight is increased then. And by this, you can store information in this memory. Yeah. So here we have a lot of spiking neurons. I didn't draw them here. But the key point is we have these two layers, which one we call the key layer and one the value layer, and we call it like this because this implements a key value memory. So what the network basically does is that it computes a representation for this key layer, so spiking, representation here, and the representation for the value layer to store useful information, which it can use later afterwards when there is a query to retrieve by activating the key layer, which will activate the corresponding, stored value layer, and this can be used to compute the output. So if you do this in this publication, we showed that you can now do things with spiking neural networks which you couldn't have done before. So for example, there are these private tasks, which are question answering tasks. There are 20 different types of tasks here, and we can solve 16 out of 20 of these tasks very well. So this goes a little bit already in the direction of more cognitive computations with spiking neural networks. Finally, I would like to talk about an application question. Yeah. So if you use a spiking network or some network in neuromorphic hardware and you apply it to some problem, then you face the following issue, that when you have your data set at home in your lab, you train it, the system, and then you deploy it at some, some application site, right? And then it probably will not work, right? Simply because there is a shift of the distribution of your data, right? The training set usually different from what you have in the real world. Yeah, this is also this real world gap that you have in neurons. So what you really would like to have is that you can adapt your system online when you deploy it, yeah, at the site of application. However, if you use deep learning for that, that's not going to work because deep learning needs a lot of training examples, and also you need quite complex training algorithms for that on your neuromorphic system, right? When we look at biology, people have proposed that actually the reason why humans and also animals are so very good learners is because they learn on several scales. There are several learning loops, so to say. Yeah, the inner loop here in this onion is when you learn a single task, right? This you want to do really quickly, right? And also in neuromorphic hardware, you want to have a simple algorithm for that. But outside, you have a loop of learning over your whole life where you can learn priors of, what's a good behavior in certain situations already, and then you can use this afterwards. And there is an even more important loop, I think, well, not more important, but a loop on a much longer time scale, which is evolution. Yeah, and I really believe that evolution has evolved brains which are very good learners for specific tasks. Yeah, so the whole structure of our brain is defined to be a fast and efficient learner, right? That's what I believe, and also others believe, like Wang in this review. So can we apply this to neuromorphic hardware? Well, in machine learning, there is also some theory for that, and it's called learning to learn, or also meta-learning. So here we can see the two loops of learning. The inner loop, where you have usually a simple learning algorithm. Yeah, you have a simple learning procedure, and you want to have fast learning. So only few updates and only few training examples are needed for learning. And you optimize here for one specific task, TI. In the outer loop, you have a task family. So there are many different tasks which are somehow related. So the tasks which you want to kind of the network should solve then typically in an application. So there are many such tasks. And in the outer loop, you have many iterations. You have more complex learning. And you choose one of the tasks of the family, and then you do an inner loop and try to optimize the weights or some parameters, some meta parameters, such that this learning is fast. And then you choose another task and do the same, and another task and another task. And by this, you kind of make sure that you want to make sure that for any task of this family, if you just do the inner loop, you get fast learning. So some colleagues, and friends from IBM Zurich, they have wonderful hardware. So we work together with Angeliki, who will also talk in the afternoon, and Thomas Ortner from IBM Zurich, and they have this wonderful Hermes chip, which is a chip which implements a crossbar array of phase change memory devices, so memoristic devices based on phase change memory technology, and we wanted to see whether we can do this learning to learn on such hardware, really using the hardware for that. We used different types of learning to learn algorithms. So this is one of those, which is, I go back to EPROB now. This is natural EPROB. It's a variant of EPROB. This is the equation. It's the same equation as before. We still have the eligibility traces here at the synapses in this network. This is the trainee, that's how we call it. But the learning signals are actually generated by a different network, which is called the learning signal generator. And now in the outer loop, in the meta-learning, you optimize the learning signal generator to generate useful learning signals such that you get fast learning of the weights in this trainee afterwards. So this is, has been done by Scher et al. This algorithm has been proposed by Scher et al. So how can we use this? Well, we used it in a robot, a simple robot control task. So the trainee has two outputs, which outputs angular velocities for two joints of this robot. We use the real robot for that, actually. What we do is, first you show a trajectory here, and then the learning signal generator computes learning signals, which are used to change the weights of this network. And then afterwards, you run this trainee network, and you want that the robot performs this trajectory, right? So the trajectory shown here is shown in Euclidean coordinates, yeah? But here you produce angular velocities to control the robot. And you want, in the end, that a single update, actually, a single weight update, this network can learn to produce any of the possible trajectories that you can have. So we did the training of the system first in software, of course, because the outer loop training you need like 10,000 or 100,000 of iterations. Where we have a simulated robot, and we actually use a standard spiking neural network here. Yeah, we don't really model the memoristic weights in any way in this outer loop training. Yeah, after we have done this, we port the network to this crossbar array, or the network weights rather, to the crossbar array. And then we do the inner loop on the hardware, which means we initialize the weights to what we have had before. And then we do one update using these learning signals of the weights. The update is done on hardware, so we have plasticity where we change the weights on the hardware. And then we run the hardware to produce the trajectory. And for me, it was quite surprising that this works really well. So here is an example. We have a target trajectory in Euclidean space in black, and the trajectory of our robot, the ED scorebot, is in green, and you see it's pretty close. So this has been done by Horst Pechanik and mainly Thomas Ortner also. So what is really remarkable here is what I said before. When we do this meta-learning, we actually don't use a model of memristors. We just train in software with full precision, 42-bit weights. We port that on PCM hardware, which has much less precision. It's noisy, and you basically equivalent of 4-bit precision. Still, it works. So you don't need to have an elaborate model of your hardware when you do the meta training. You can just train it on a vanilla model, and it will still work. It's not so clear to me why this works, but potentially this meta learning kind of really gets a very robust system. You can do this also with other types of networks. So here we had a convolutional network, and the task was omniglot, few-shot learning with 3 training examples, and then classify the class. Again, we did actually compare here to a hardware-aware training where we used 4-bit precision of the weights, but the performance were very similar. And you see the performance of the neuromorphic hardware with is very close to optimal. Okay, so let me conclude. Yeah, I was talking about evolution of spiking neural networks and some advances there. We started out with live neurons when we start with spiking neural networks. Surrogate gradient was really an important step there. Now we can train spiking neural networks. We also have online algorithms to train spiking neural networks. I think that looking at kind of alternative neural models turned out to be really fruitful, like resonator neurons. And I also think, so this is kind of at least my direction where I think one should go, is that looking at specific computational structures that you add to your network structure is really important. So we've seen that a very simple example, just adding this memory a layer to your network really improves its capabilities. And if you look at the brain, you see that there are so many different structures that are optimized for different types of computations. It's not just a random recurrent network, what we currently use, but there is so much structure there, and I think we should exploit that in our networks for computation. So with this, I want to thank the people who did the work, the collaborators, and the funding. Thank you very much.
Thank you very much, Robert, for that really interesting and comprehensive coverage of the development of spiking neural networks that do useful things. That was really interesting, and I think you've filled in some gaps for me as well that I was not aware of. I'm sure we have some questions. Please, over here.
Thank you, Robert, for a fascinating talk. I was wondering whether you have explored the meta-learning approach more using Heppian-like learning rules, which are more biological inspired, and whether that also produces some good outputs like EPROP, or what do you think about that?
Right, it's a good question, actually. So I don't have the slides anymore, but when I was talking about the convolutional network, here we use the meta-learning called MAML, model-agnostic meta-learning. And actually what I didn't tell you is that we only trained the output layer of the network, because this is like much better in terms of the hardware implementation. And here you get back to a very simple update rule, which is kind of Heppian, but you have, of course, a supervision signal there. So it's already something which where you get a very simple learning rule in the inner loop. Another thing I want to say is when I talked about these memory networks that we did, that here this can also be seen as a kind of meta-learning actually, because you do an optimization where the network really learns to use this Heppian plasticity rule in the optimal way. So it's already kind of a meta-learning. I think this is a very good idea. One can use meta-learning also to optimize the network to use very simple, unsupervised, let's say, plasticity rules like Heppian learning, SDB even, or something like that. Absolutely.
Thanks. Over here, please.
Thank you very much for this super interesting and broad talk. I'm David and Blanco from TU Delft, and I have a small story and then a question. So at the start of the 20th century, people were trying to build flying machines. And they started building feather-like structures and flapping wings. They jumped off the Eiffel Tower with it. Well, and you can imagine how that ended. And then in 1908, the Wright brothers came along. They put together a small engine, a bike chain. They did the math for the wings, and they managed to take to the skies and build the first working aircraft. And since then, we've developed planes that can fly faster and higher. And basically, all planes today, they still have the same structure and layout as the original plane. And so I was wondering, what is your take on using neuromorphic computing in this space? Because we're being very bio-inspired. But as we've seen, the final application is not exactly the same. I mean, birds are 200-gram animals. We want to transport thousands of kilos and hundreds of people. And another example could be that, for example, nature never invented rotating locomotion. So what is your take on this? How bio-inspired should we be? And should we be beyond bio-inspired at some point? Thanks.
Yeah, so this is a question which concerns everyone in the room, I guess, and everyone has thought about it. I'm assuming many people have thought about this question. Should we really go for this bio-inspired thing, and how far should we go? So I'm not really, what should I say? So my opinion is that, I mean, in general, you should do what works, right? And it really turns out that in the end, what works will be used. Yeah, people don't care whether it's bio-inspired or not, as long as it works, right? And this is also the, of course, the success of deep learning, which is to some extent also bio-inspired. You have to say it's a neural network, right? It has the basic structure of the brain, but should we have like get closer to the brain? Yeah, I think that it has advantages to get. So, for example, for spiking neurons, we all know it's kind of it has become the main model for neuromorphic systems, and we see the direct advantages. It's more energy efficient in general, and so it has its advantages, and that's also why we use it, right? If we wouldn't believe in that, then we wouldn't work on this. So then further, should we go like further in our bio-inspiredness, right? I think yes, and the reason why is because the brain always gives us great ideas. If we look at the brain, it gives us great ideas, right? So if convolutional networks, for example, yeah, the structure is the structure of visual processing in cortex. Also transformers to some extent, attention mechanisms. Attention is important. Of course, it's very abstract and it's kind of not the same. I agree. And I think that, of course, we haven't solved the problem of artificial intelligence. We've seen this also yesterday. People said this, transformers are not the solution. So we should further look for inspiration. If it works out, we will see. Yeah.
Thanks.
But I'm not dogmatic on this, of course. Yeah.
I think probably we shouldn't be dogmatic, right? I mean, if we knew which direction the solution was going to be in, then we would already have the solution.
Absolutely.
So we need to take the ideas and the concepts wherever we find them, and it would be foolish of us to ignore the brain, and it would be foolish of us to focus entirely on the brain.
Absolutely, I agree.
Do we have any further questions for Robert? So I have one. I would like to invite you to speculate. You demonstrated very effectively the increase in capacity that we have when we take more concepts from biology, when we go from like the very simple activation function to a more sigmoidal one, to including some concept of neuronal structure, to including specific structures. So if you were to look ahead, what do you think is the biggest thing that we're so far ignoring that we should take into account?
Wow, this is a really hard question. I'm not sure I can answer this question. But I think if we look at the brain, I think that we have circuits which, for example, which are optimized for reasoning, for example. And this is something one should look into, at least, because reasoning is really important in intelligence, and it's not used in any artificial system currently. And so this is one example where I would see something which could be integrated. But I really don't know. I mean, I'm sure there will be a lot will come up very soon in this direction.
Okay, thank you very much,
Okay.
and thank you for your presentation today.